sections that may discuss things that we did not have time to discuss in class. They're all discussed in the book. Not all lectures have an associated book chapter, but those that do, you see it on the web page. Yan has printed copies of the assignment for you, but they're also available online. Did the email message go out? Not yet? Okay. I'm sorry?
I haven't figured out how to send
okay.
email list.
We should be sending you a welcoming message to the email list today or tomorrow, I suppose. There are still quite a few people on the waiting list, and several of you have written to me about it. I hope that I can let everybody in, but we won't know until probably the end of this week. So please hang in there. Of course, our mailing list includes the people who are on the waiting list, so you get any announcements that will go out. As soon as I know whether I can let everybody in, I will, of course, let the people on the waiting list know. Okay. Today we're going to finish discussing concept learning. If you remember, we defined concept as a function that maps from the input space to yes or no, and concept learning, the process of using examples to zero in hopefully on the correct target concept. So I'll give you again the formalism we have been using and will continue to use. X is our input space. We discussed cases where X was an image. It could be a sentence, it could be an acoustic wave sign, it could be a bunch of numbers, or it could be a set of attributes, as in the case we discussed in class. Small c is our target concept. As any other concept, it's a function. Function from X to yes and no. Small c comes from a space of all possible concepts, which I call big C or curly C. This is our concept space. The important thing to remember about it is it's very, very big. The size of C, namely the number of possible concepts, is 2 to the power of the size of the input space. The input space itself is typically exponential in the number of bits or attributes or whatever it is in it. So we end up with a doubly exponential concept space. But in the general case, it's just singly exponential in the size of the input space. The next thing we have is data. Call it D, training data. And it comes in pairs. Whoopsie. Each pair is of the form x1, which is a particular instance, a particular member of the input space X, and the correct classification of x1 into yes or no. We can depict that with C of x1, because C is our target function. This is one pair, and then there are many other such pairs, and in the end we have the nth pair, xn and C of xn. x1, C of x1, x2, C of x2, and so forth. Sometimes we might call C of x1 y1, and C of xn would be called yn, small n. The important thing to note is that we know these values, but we don't know C. So we know the value of C on specific inputs, but we don't know the general form of C. And therefore we don't know the value of C on all possible inputs. If we knew the value of C on all possible inputs, then we effectively know C. And vice versa. If we know C in some kind of functional form, we can in principle calculate its value on all possible inputs. This is worth thinking about for a minute, because one way of specifying C, some ways of specifying it is by rules, maybe polynomial, maybe some if-then rules. There are many, many ways you can specify functions. But one way of specifying a function is by explicitly enumerating its value on all possible inputs. That is a perfectly legitimate representation for a function. So if you're thinking of learning C, we typically think of learning a concise or compact representation for it. Learning, in a reasonable way, some description that can be applied to any input. But it's also possible to just enumerate all the values that C takes and all the inputs, and that's, C that way. If the input space is too large, maybe you can't do that. Turn this down a little. Questions so far? Okay, in the example we looked at last time, we had one more concept, and that was we defined a language for representing possible hypotheses. Remember, the language consisted of those angled brackets, and in between them we could put in each attribute position either a particular value or a don't care symbol. Remember that? So let me give you the example here. The enjoy sport problem X was a set of all possible weather patterns as expressed over 6 attributes. Remember those attributes? The first one had 3 possible values. I think the sky could be sunny, cloudy, or rainy. And then there was temperature and wind and all that, and they all were binary. So X was a set of 3 times 2 times 2 times 2 times 2 times 2 attribute values. And as a result, the size of X was 96. C, we don't know what C is, but we were looking for some way of expressing the target function, which is the weather conditions under which I enjoy sport. I will go out to the beach and surf. The concept space was a space of all possible functions from these 96 possible instances to yes or no, and there are 2 to the 96 such values, very large number. And our data consisted of only 4 examples. X1, C1, X2, C2. In fact, I even know that C1 was yes, C2 was yes, C3 was no, and C4 was yes. Remember, the first, second, and fourth examples were positive. So this is our data. And now we introduced a new concept, which was a language for describing possible concepts. And that language consisted of these angled brackets with 6 positions. And each position you could specify either a particular value that must be true or a don't care. And this defined for us what we call the hypothesis space. A space of hypotheses that we will consider. The hypothesis space we'll designate with H for hypothesis. What's the relationship between H and big C? H is a subset of big C, always. So H is a subset of C. Could be the entire set, that's also a subset. But typically, H is a very, very small subset of big C. So in our particular case, let me first write here H, hypothesis space, subset of C, of big C. Now in our case here, what was the size of H? If you remember, we counted in the binary attribute you could put 3 possible values, either hot, cold, or don't care. 3 possible values here, 3 here, 3 here, 3 here, 3 here, and 4 here. Multiply them through, you get 972. Then you have to add the hypothesis where nothing is allowed. That's the don't care, the null symbol. If you put a null symbol in any one of these positions, you might as well put them everywhere, because a null symbol in any one of the attributes means that every input the answer is no. So multiply this together and add 1, and you get 973. Compare this to 2 to the 96. It's a tiny, tiny fraction of the space. You guys gave me arguments. You showed me what kind of functions are not included. Some functions are not included. You talked about or, right? This attribute or this attribute. You know, the sky is sunny or the temperature is high. Cannot be expressed in this language. And because it is such a tiny fraction, if you take a random function, there's a very high likelihood, 99.999%, that it cannot be expressed. So the vast majority of functions cannot be expressed in this formalism. Is that good or bad? Shall we choose a formalism where you can express everything? Please.
It's bad because if the training data is random, and there isn't necessarily any correlation between your training data, then you're never going to get the correct function.
It's bad because if the training data is random, you're not going to get the correct answer. And you're not going to get the correct answer because the correct answer is not in the space we're considering. Is that what you're saying? So I would agree with this last part, that if the correct answer is not inside H, there is no way we're going to get it. Right? So we're right at the outset throwing away a lot. So let's draw that. Very abstractly, this is the space of all possible functions, big C, and we chose to concentrate on this little point here, which is H. And we're only considering functions that are here. Well, what if the target function is here, or here, or here? We are guaranteed to not be able to find it, because we cannot express it. Do you have a comment?
We might be okay wanting something that was close, though.
Aha! Maybe we will find something close. So maybe this is not the right picture. Maybe the right picture is that H contains members that are spread throughout the space. Maybe all these points that I marked are part of H. And there are many, many other points that are not part of H. But whatever the true function is, there's an H point not too far from it. What do we mean by not too far? We mean that they mostly agree. They might disagree on a few examples, but they mostly agree. Was that the intuition? Yeah, so it may not cover the whole space, but the fact that it's small doesn't mean that it's not spread out or that you cannot find an approximation. But it certainly means that if the target function is not in that set, you cannot find it exactly. Okay, so why even choose a hypothesis space that is smaller than the full, why not consider the full constant space? Why not make H equal C? Please? It's almost too large, and it's too large.
Possible to really learn something from it. Because the hypothesis that you see is like you enumerate all examples. It's not learning something new.
You're saying if you use H equals C, it is too large and it's almost impossible to learn in it. You'll be enumerating. Okay. Is that a problem of computation? Should I just get a bigger computer? Suppose I did have a computer that could process 2 to the 96 possible operations a second. Okay.
But you still need more training data.
Can you speak louder, please?
You still need more training data.
You need more training data. So you see a relationship between the amount of training data and the size of H that you're considering?
Yeah.
Okay. Anybody want to agree or disagree, please?
Maybe we start learning something very specific to the training data itself. If we're trying to get an exact fit, maybe that's not true.
Okay, you're saying that if you don't have enough data relative to the size of H, you might learn something that's specific to the training data that's not general. Is that what you're saying? Or am I putting words in your mouth?
Yeah, and that suppose we're trying to make H equals C, then we're actually, I think we're trying to learn something really specific. We don't have to cover the whole C.
Okay. All right. Any other comments here? Please.
Cover all C, that might mean that you just have two values, yes, one yes and no for same values attributes. Basically you're covering all the possible values.
I'm sorry, I didn't understand it. If you cover all of C,
If you cover all of C, then that means for same attribute values, you might have both function that maps to yes and no. So
you're saying that if you consider all of C, you would have for the same input both a yes answer and a no answer.
yeah.
I have to disagree with that. You're right that there is the possibility of functions that are stochastic, that for the same input sometimes will give you one answer, sometimes will give you another. But I exclude them here. When I talk about C, I mean only the space of deterministic, non-changing concepts. So any member of C gives the same answer, always gives the same answers, and for the same input it would always give the same answer. So you will not have a situation, if it gives two different answers for the same input, then it's not the same concept of C. It's two different members of C. So it's a valid point, but I'm excluding it here. Any other comments about why we choose H, or why we choose a small h, or what are the pluses and minuses? I'm sorry? So we can
model, because it's not possible sometimes to model a bigger, before C. So if you want to solve the problem, so we kind of are satisfied with something you can solve.
So you're saying it's a pragmatic consideration. You have to do it to get somewhere.
Right. I mean, it's desirable, I think, to find the whole space, but if you can't, then you break down the problem to something you can manage.
Okay. Do you have a sense in the specific case of Enjoy Sport, that a priori, before you saw any data, just by hearing about the nature of the problem, that some concepts are more likely than others? So I'm telling you that it's about whether you enjoy sport or not, and that it depends on the water temperature and air temperature, and you might expect that when the water temperature is warm I enjoy it, and when it's cold I don't. But you wouldn't be surprised if I told you it's actually the opposite. I like cold water. You also wouldn't be terribly surprised if I told you I don't care about the water temperature. So all three are possible. But try not to combine water temperature with forecast for the next day, if you remember that's one of the attributes. You might think that if I like warm water temperature more than cold water temperature, that fact should not depend on whether the forecast for tomorrow is change or the same. At least my relative preference between cold and warm should not change, should not reverse. You might be able to put some constraints a priori based on your knowledge of sports and of what people like. Now, they may not be 100% guaranteed, but I can imagine giving you a concept, an example concept that you say, this concept doesn't make sense. It looks random. It looks like you don't really have any rule. So you might have a preconceived notion of some rules being more reasonable than others for the situation, more likely than others. So this is something you might want to bring to the table when you think about what H to choose. We're not done talking about this. In fact, this is the heart of machine learning, but let me give you the terminology for it. The choice of H, namely the choice of a subset of the space on which to concentrate, on which to look for a solution, is called a bias. The bias of a learning system is basically the preconceived notion or preconceived decision to concentrate on a typically very small subset of all possible solutions. There are several ways of introducing a bias. We introduce a bias by creating a representation or a language for expressing concepts, and that language was only able to express some concepts and not others. Right? I introduced this language with angled brackets, and just by introducing it, I implicitly ruled out most of the concepts in the space, and implicitly kept only those that can be expressed by it. That kind of a bias is called a language bias or a representation bias. Whether bias is good or bad, or a necessary evil, we will talk about more. But for now, I just want you to recognize it in every situation we discuss and ask yourself, what is the bias here? Either the bias that somebody else introduced, or you're going to introduce your own bias. You may ask yourself, how strong is the bias? Namely, how small is the set that we chose? This bias also goes by the name, I prefer, hard bias. Hard bias because it makes a very abrupt decision what to include and what to exclude. We will discuss at a later point a soft bias, whereas instead of making this all or none decision, which concepts to keep as candidates and which concepts to not consider, we make a more gradual decision of which concepts to pay more attention to, consider first, give more likelihood to, and so forth. Sort of a more grayscale kind of view. They're both called bias. How do you choose your bias? How do you choose which concepts to keep and which not to keep? Well, we discussed right now a few things. Preconceived notion, coming into a problem and saying, I think this is more likely, I think this is less likely. Pragmatic considerations, I cannot handle so many, I must handle fewer. But whatever your reason, when you introduce a bias, you introduce a possibility of failure right away. Because if you chose it wrong, and the correct target function is outside your space, you will never find it. And if in addition there is nothing inside your hypothesis space that's even near, that's even similar to a target concept, then you will not find even an approximation. Questions? Please.
So the biases we choose themselves must be likely, and they must be as dissimilar from each other as possible. incorporate both these steps.
You're suggesting that you should choose a hypothesis space where the members are quite far apart from each other?
Yeah, and also that they are by themselves likely.
So you're saying let's choose a H hypothesis space consisting of concepts that are plausible to start with and maximally different. That's reasonable. But there are often many other pragmatic considerations, like how do you represent them, how do you search through them, and so forth. But that's a fair criterion. I want to mention one other general thing, and that is that when we talk about concepts as functions, we can also think of concepts as subsets. It's one and the same thing. A concept can be identified with that subset of the input space on which the concept says yes. How many subsets of a set of n items are there? 2 to the n. Exactly the same number of functions from that space to yes or no. So keep that in mind. Concepts are subsets, concepts are also functions. Now, the example I went over last time was of this problem with a very simple algorithm that has a very specific bias. In fact, it has two kinds of bias. The first bias is by sticking only to this H, to this language with angled brackets. That's a huge bias right there. It's a hard bias, a language bias, or representation bias, because it really shows a tiny space of 973 concepts out of the very large space of 2 to the 96. But after it shows this, it further introduced another bias, which is, if you remember, the algorithm started with the most conservative hypothesis, the one that said no to every input. That's the hypothesis that's represented by these null symbols. And as we went through the positive training examples, we relaxed these constraints. First, we replaced them by attribute value of the first positive example, and then some of these had to be further relaxed and converted into a don't care. Remember that? Nonetheless, you get the sense that this algorithm wants to say no to everything it can. Right? Think of it as a grumpy old man that just looks for opportunities to say no and just reluctantly says yes if it has to. But you can imagine an identical algorithm, sort of reversed, that is the opposite. Wants to say yes to everything. Yeah, of course, I'll enjoy, I'll go to the beach, I'll swim, no matter what. Unless it is faced with some negative examples, then it must start qualifying and restricting what it says yes to. These two algorithms, faced with the same training examples, will end up in two different places. So they each have their own additional bias. Beyond the representation bias, or language bias, they have a soft bias or a preference bias, where they prefer some hypothesis within H, they prefer some hypothesis over others. The algorithm we went over in class, called find S, prefers the hypotheses that are more conservative, that tend to say no. The alternative one prefers those that prefer to say yes. And you can think of other kinds of biases. Let me briefly put up the slides with the visualization that I'd like you to have. Okay, what we have here is the two spaces we've been talking about. The input space X on the left, or sometimes called instance space. Instance and input are the same thing. Or the hypothesis space H on the right. Every point in the hypothesis space corresponds to a subset of the input space. This traces the little algorithm that I showed you last time, where you start with the most specific hypothesis and you relax it as you see more and more positive examples. I think I have another version of it that shows H0. Yeah. I'll give you this one instead. The algorithm starts with what we call H0, which is the hypothesis that says no to everything. It corresponds to an empty set in the instance space. So here's H sub 0, and you see it has nulls everywhere. We're then exposed to the first positive training example, which forces us to convert all of these null symbols to the specific values here: sunny, warm, normal, strong, warm, same. Notice there's a difference between this row and this row. This row is an instance, this row is a hypothesis. Actually, this should not have the angled brackets here. Angled brackets belong only to instances. I should change that. I apologize. In the picture, we were forced to move from H0 to H1. H1 corresponds to this set, which is exactly just a member X1. I'm going to try. Okay. So after seeing the first positive instance, we were able to relax our constraints minimally, just to include this one instance and nothing else, which this algorithm loves to do, right? It doesn't like to say yes. Then we see a second positive example, and as we go item by item, we'll see that it differs on the third attribute and the third attribute only. So the third attribute becomes a don't care, which corresponds to increasing the subset from covering only X1 to also covering X2, which corresponds to hypothesis H2. We skip over the third example because it's negative. The algorithm ignores negative examples, so H3 is the same as H2. And then when we get to the fourth training example, which is positive, we find that we have to generalize two more attributes to don't cares. This corresponds to taking two steps here, and now we have H4, which includes X1, X2, X4, and, as you guys pointed out last time, it includes some other members that we did not explicitly want to include. Why did that happen? Because there's no way within this language of angled brackets to represent just X1, X2, and X4. So it's a direct consequence of our representation bias. Or you can think about it as direct consequences of the language we chose to represent our concepts. So there's nothing wrong with the algorithm. It is true to its mission of saying no to everything it can say no to. But it cannot admit these three positive examples and continue to say no to everything else. There's just no such function within H. There are such functions within C, but not within H. So what we got here is implicit generalization. After seeing these three positive examples, the algorithm now says yes to these as well. If we chose a different representation, maybe one that used OR instead of AND, or that allowed some other combinations, maybe this would not happen. Some other generalization would happen. Now what if we chose a representation that allowed all functions, namely H equals C? How would these subsets grow? Please.
slowly, one by
slowly, one by one. You would want to include another positive instance. There will be a function that includes it, right? Because by definition, all functions are allowed. All possible subsets are allowed. You can start to see from that if you don't have a hard bias, it is hard to generalize. You will not get generalizations. Saying something about some instances will tell you nothing about others, or will push you in no particular direction about others. So the whole essence of generalization of how can I learn from these examples about these examples is tied into the bias. When you have a bias, then knowing the value of some instances tells you something about the values of others. You can think about it as a crosstalk between instances. When you don't have a bias, you don't have crosstalk. So far, I recommended that you introduce some kind of a bias and go with it. Even if you do that, if you introduce the hard bias, there is still the problem of the soft bias. Namely, within H, what do you choose? Given H, as in our case, and given a small number of examples, there are still many functions, many concepts that are within H and that are consistent with the training examples you've seen so far. Which of these should you choose? The find S algorithm says choose the most specific one you can, the most conservative one. Another algorithm might say choose something else. Yet another possibility would be not to choose. To try to keep track of all the functions that are in H that are consistent with the training examples you've seen so far. If you do that, that concept of all functions in H that are consistent with what you've seen so far is called a version space. A version space, I don't know why I put H here, it should be S, is a function of two things. It's a function of the hypothesis space you started with and the data you've seen so far. So you can think about it as a function of two arguments. If you think of this as all of C, and let's say H is this, and this is very misleading because H is typically a much, much smaller subset of C. But just so that you can see it on the board, I drew it bigger. But remember that H is usually a tiny fraction of C. If this is H, after seeing 4 training examples, you're able to rule out any member of H that is inconsistent with at least one of them. And you are left with some subset of H, call this VH, version space of H and D1 through D4. The 4 training examples. All the members of this set are, in some sense, equally good. In the sense that they're all part of the H that you chose, and they all agree with the training data. They're all consistent with the training data. Now suppose you get a 5th example. That 5th example might disagree with some of the predictions of some of the members of this set. So any member of this set that disagrees with the 5th example, that says yes when the 5th example is negative or no when it's positive, will be ruled out. and the version space will shrink. So the next version space might be something like this. Now you get a 6th example, and a 7th example, and an 8th example, and the space can get smaller and smaller and smaller. So this, you can think about it as a shrinking process, that as the amount of data gets larger, the space shrinks. At any point you can stop and say, okay, I'm not going to see any more data, what do I have? And the answer is you have a set of functions that all look equally good. And now what do you do with them? Which one do you choose as your answer? I'm sorry?
All of them.
All of them? How can you choose all? Well, I guess you can give the entire version space as the answer, yeah? That's fine. But what would your boss do with all of them? So you were given an assignment to learn a function from data, and instead of coming back with a single function, you come back with a whole set of them and say, here's the version space. Okay, what could it be used for?
I think your question is to introduce files again, like in Farnet,
Uh-huh.
to find some function within version space, and the other is to give data functions all in version space and for a new instance, that all the functions in the version space to decide on this instance and assemble the output together, like voting.
Okay, you introduce voting. That's interesting. So you're saying your boss gets this set of functions from you, and they don't know what to do with them because they were looking for one function, but if they're looking for a particular prediction, they can just take a vote among all these members. Okay? Or you can introduce another bias, as you said, and choose one on some other principle, like the simplest, the shortest, the most negative, the most positive. Okay? Suppose you could create more training examples. It's up to you to find new instances, or to select new instances and get the answers for them and add them to your training set. How would you go about choosing instances to shrink your version space maximally or fastest? Choose one that does what?
That will rule out most functions in my version.
That rule out the most functions in version space. Okay, and how would you do that? Please. The one with the most disagreement. Okay, so if you can find instances that are kind of surprising to the majority of functions, that'll rule them out real quick, right?
Well, right, but you don't want something that most things would disagree with and say maybe they'll disagree with this because chances are that you want to try to split your version space.
So if you know in advance what the correct answer is, you can look for a surprising answer. But if you don't, maybe you look for a function on which there's the most disagreement within the set, namely that the votes are split more or less half and half. So I'll tell you another one of my little kid story. I used to play with my kids the 20 question game. You choose a number between 1 and 100, and the other person has to guess this number by asking, is it larger or smaller than 37? And when my daughter was 3, she would say, well, okay, is it larger or smaller than 18? And I say larger. And she'd say, okay, is it larger or smaller than 19? And I'd say larger. And she'd say, okay, is it larger or smaller than 20? And I was dying to tell her, no, you're not being efficient, but that's not what she was learning. Now, why is that? Why are we more efficient when we split the space in two? Turns out we're not necessarily more efficient, we're just more efficient on average. So we will get to that when we talk about information theory. But there are ways of proving that on average you will get there faster, or you will shrink the space fastest if you ask questions that split the vote into that. They're about roughly equal sides on both sides of the question. Roughly equal number of functions saying yes and saying no. If you ask a question for which there's a skewed distribution, like 90% saying yes and 10% saying no, then 90% of the time you only got rid of 10% of the population, and 10% of the time you got rid of 90% of the population, which is very nice. So when are you better off? Having 90% chance of getting rid of 10% and 10% chance of getting rid of 90%, or having 100% chance of getting rid of 50%? It turns out on average you're better off with the second case. But it's not so trivial to prove. I will show that to you. Please.
I don't think that's quite true, because in the training examples, no distribution of yes and no's. So if you have a new training example, it could be 50-50. Yes, no. But if you look at your version space, 90% of the functions say yes and 10% say no.
Yeah, I was referring to the distribution in the version space, not in H or not in general, just in your version space. And sometimes you don't know in advance what the distribution will be. You're quite right. But if there's a way for you to quantify, if you look at your version space, if there's a way for you to find questions on which there is maximal balanced disagreement, you should try to pose these questions. Okay, there's one other problem with this notion of keeping track of version space. A very pragmatic problem. Can you guess what it is? Version space can be very, very large. I mean, it's always smaller than H, and H in our example here is only 973. But in real-world situations, it could be an exponential space. Very, very large. Which means that computationally, keeping track of it may not be possible. Imagine an input space that has 10 billion bits or pixels, a concept space that's 2 to the power of that, a hypothesis space that's much smaller than that but is still very exponential, and then you look at 100,000 training examples, and that leaves only 10 to the 300 possible solutions in your version space. You cannot keep track of all of them. Sometimes you can keep track of them implicitly, and I'll show you how you do that to the rest of this time. So, example of the version space that you get if you start from the H that we defined with the angled brackets, which has 973 members in it, and you introduce the 4 trading examples that I showed you, 3 positive, 1 negative. I won't go through the details, but I hope you take it on faith that this is what you get. There are 6 members in this space. 1, 2, 3, 4, 5, and 6. Every angled bracket creature is a member of the version space. You can convince yourself that these 6 functions are consistent with the training data. It'll be a little harder to convince yourself that there are no other functions that are consistent with the training data that fall in this space that can be represented in this language. Now, I didn't just list these 6 in a row. I put them in a lattice of relationships, the way I showed you in the previous picture. And this lattice has the same kind of inclusion relationship. These arrows. This arrow means this is more general than this. More general means anything that this says yes to, this definitely says yes to also. But not necessarily the other way around. The other direction is called more specific then. Function f is more specific than function g if every time function g says no, function f also says no. So you can think about being more general as being more permissive and being more specific as being more conservative. In the language of subsets, more general then means being a superset of. More specific then means being a subset of. These are all the same relation. You can take any set of functions and try to draw these arrows between them. Who includes whom? Who is more general than whom? This relationship of being more general then is not a complete relationship in the sense that every two members must be related. It's a partial order. If you have a set, some members are related, others are not. For example, these two are not related to each other. In the language of set theory, they have partial overlap. Neither one completely subsumes the other. If we were to draw these six, the relationship between these six concepts in a Venn diagram, the one at the very top would be inside. Maybe I should do that. The one at the very top would be inside. Then there would be three supersets of it. 1, 2, 3. These three supersets don't completely include each other. That's why there are no arrows between them. And then there are two that include all of these. So there would be something like this and that. I don't know if you can make sense of this, but it's easier to see here. This is also called a lattice. A lattice is a partial order on elements of a set. A partial order that satisfies some rules, like if A is more general than B and B is more general than C, then A is more general than C. So there's transitivity, reflexivity, and antisymmetry. These are the three conditions that are required. Okay, here's our version space. Now the interesting thing here is that we can identify the boundaries of the version space. The thing we put in the black box there is called a specific boundary. It consists of all the hypotheses that are maximally specific in this version space. Maximally specific means there is no other hypothesis in the version space that is more specific than these. It turns out there's only one, but it's still a set of one. If you look at this one, this is called the general boundary, or the general front, and this consists of all the hypotheses in this lattice that are maximally general. Now here's the idea. When the version space is very small, like this one, it's no big deal. There are two hypotheses here, one there, and three here. We can write them all out. If the version space is much, much bigger, the number of elements here and here still can grow linearly, or at least be kept under check. Whereas the number of hypotheses here grows like crazy, exponentially. So, if we can keep track of the entire version space by only keep track of the most specific front and the most general front, then we're effectively manipulating the entire version space without having to list it, without having to go over every hypothesis specifically. Whether we can do it or not depends on the specific details of the hypothesis space. In the case of this hypothesis space, of this language, the answer is yes, we can, and I'll show you how it's done in an algorithm. But in general, what I want you to get out of it as a high-level concept is that version spaces are useful ways of thinking about generalization. Once you chose your bias, you're restricted. Once you chose your hard bias, you're restricted to some space H. Once you see examples that shrinks that space for you, you get a version space. At any point you stop, you still have a potentially large number of candidates that are all in some sense equally good. And if you cannot handle that computationally, explicitly, you might be able to handle it by keeping track of the extreme cases of the lattice. Let me show you the algorithm. It's a little complicated. You will definitely need to go over the book and over the details. The algorithm is called the candidate elimination algorithm. And notice that there is no variable in it for the version space itself, because the version space itself is not represented explicitly. There are just two major variables are G and S. There are two sets. G is the maximally specific set. G is the maximally general set. S is the maximally specific set. You start by setting G and S to what they ought to be for the entire space H. What is the most specific hypothesis in H in our particular example? It's the one that says no to everything, which can be represented by nulls everywhere. So I'll actually start with that. I'll call it S sub 0, and it consists of this one member which has nulls in it. What is the maximally general hypothesis in H? There could be more than one, but in our particular case there is only one. Somebody else? Please? Right. It's the hypothesis that says yes to everything, which luckily we can represent in our notation, and we represent it by saying don't care to everything. So that would be G sub 0, and it's a set. It has only one member, and the member is don't care, don't care, don't care, don't care, don't care, and don't care. Now this is a very simple form of the S and G, and notice that they implicitly capture in between them all of H. Every member of H sits somewhere here and is connected by these arrows, these more specific than, less specific than arrows, to some member of G and to some member of S. This is important. The definition of the version space, the definition of the lattice, is that every member in it is connected by arrows, by this inclusion or subsumption relationships, both up and down. Up to at least one member of S and down to at least one member of G. Why is it true? How do we know that's true? Suppose there was a member of H here, and it was connected by an arrow to another member of H and connected by an arrow to another member of H. And now this one was stuck, wasn't connected to here. Then we could say that this one is maximally specific. Right? By definition, maximally specific means there's nothing else in H that's more specific than it. And if it's maximally specific, it belongs in S. Okay, so by definition of S and G, every member must be connected to at least one member of S and one member of G, otherwise they themselves become a member of S or a member of G. Okay. Now let's look at the algorithm, see what it does, and then we will trace it with our training examples. The algorithm takes one training example at a time, call it small d, and what it effectively does is it modifies S and G to take the new training example into account. Let's first see what happens if D is a positive example. If D is a negative example, what happens is very, very similar, just inverted. Same idea. So let's concentrate on the case where D is a positive example. If D is a positive example, we need to modify both G and S. It turns out it's very easy to modify G, it's a little more difficult to modify S. If D were a negative example, it would be the other way around. So if D is a positive example, we look at G, we'll ignore the example now, we just look at the general case. G may have multiple members, and all we have to do is find those members of G that are no longer consistent, that no longer belong to the version space, and throw them out. And we don't need to do anything else. By throwing them out, we're implicitly throwing out any chain that starts from them. And any member, unless that member connects to some other member of G. So when would it happen that G would be inconsistent with the training example? Since the training example is positive, it would happen if some member of G fails to include that training example, fails to say yes to it. Then out it goes. So G might become smaller. Now we take the same training example and we look at S. And again we search all the members of S, of which there could be 1 or 2 or 3 or many more. Search for the ones that are inconsistent with D. What does it mean for it to be inconsistent with D? Again, since D is positive, it means that that member of S failed to say yes to this example. But now we're not free to just toss it out. Instead of tossing it out, we have to replace it by minimal generalizations. Because that member of S stands for being very conservative. And if it cannot remain in the version space, it should be replaced by its direct children that are slightly less conservative. So we need to remove an inconsistent member from S, but add back to S all of the minimal generalizations of which, such that they are consistent with the new training example. They are connected to G, so some member of G is more general than them, so there's a way to connect to G, because if there's no way to connect, it should not be in the version space. And then we have to do some housekeeping. It might turn out that after we replace some member of S with some other members that used to be inside the version space, that some of the members of S are related to each other. One is more general than the other. And since S has to be only maximally specific members, we get rid of the ones that are related. So if you find inside S 2 hypotheses that are related by an arrow, you eliminate this one. This is the arrow of more general then. So think about it at a very high level as just removing from the version space things that are not consistent with the new training example, and then doing some housekeeping in S and in G to make sure that they continue to be the maximally specific front and the maximally general front. Again, you need to read this in detail and go over the examples to get it. What I'm trying to do now is just to give you the high level idea. Let's do a trace of it. That might give you some of the detail you need. I'm not going to go over the rest of the algorithm. The rest of the algorithm is here. If D is a negative example, continue to the next page. It's in the book. It's very similar to this, but with S and G reversed. Here are training examples, and let's use them to trace this algorithm. We started with the full version space, and with S sub 0 and G sub 0. Now we have our first training example. It is positive, so we're going to do the first half of the algorithm, the one that I showed you. We're starting with modification to G. Remember that positive examples are easy to work on G, more complicated to work on S. Negative examples are the other way around. So we have a positive example. It's easy to work on G. All we have to do is throw out anything that is inconsistent with that example. Is there any member of G that is inconsistent with the first training example? No. First of all, there's only one member of G. And second, it's the one that says yes to everything. So of course it's consistent with the positive example. So we don't need to do anything to G sub 0. And therefore G sub 1 is equal to G sub 0. The G front, after seeing one example, is G sub 1. And it's the same as G sub 0. Now let's go to the S. We need to eliminate any member of S that is not consistent and replace it with minimal generalizations. Are the members of F sub 0 that are not consistent with the first training example? Yes, there is only one member, and it is definitely not consistent because it says no to everything. So we need to cross it out and replace it with all minimal ways of being consistent. Minimal generalization. How do we do that? That actually depends on the specifics of the version space. Okay? Up to here, we talked generally. Any version space, any G, any S. Now we need to talk nuts and bolts. How do you find minimal generalizations? Go ahead.
Right now you can use the training example.
Yeah, just the hypothesis that corresponds to saying yes for this training example. That is clearly the shortest, minimalist generalization. You're only letting in one training example, nothing else. Luckily, we can still do that. So it would correspond to the first training example, which is sunny, warm, normal, strong, warm and staying. Luckily for us, S still has only a single member. Okay, we're done with the first training example. Let's go to the second training example. The second training example is also positive. So again, we execute that part of the algorithm that I showed you. First we go to G, identify any inconsistent members and throw them out. Are there any inconsistent members? No. There's one member and it says yes to everything. So G sub 2 equals to G sub 1 equals to G0. No changes there so far. Now we go to S, the latest S we have, and we identify members that are inconsistent with this training example. There's only a single member. Is it consistent with the second training example? I want to see everybody shake their head. No. No, this hypothesis says yes only to this particular combination of values and says no to everything else. The second training example has some different values. So this hypothesis says no to it. So we must now find the minimal way of generalizing it so it says yes to it. And if there's more than one such way, we should include both of them. What's the minimal way to generalize this so that it says yes to the second training example? Please. Okay, so you S sub 2 would be, this is the same form. Normal becomes don't care, and then strong form, same. Are there any other ways of generalizing? Please.
Question, but what if you do care? What if you only accept normal and high, and not low, for example?
If you only accept normal and high, assuming that humidity had more than two values. Okay, humidity has only two values. Okay, now this is a very good question. Suppose humidity had more than two values. It had normal, high, and low. What do you do then?
You still have to say don't care because of our representation.
You still have to say don't care because of our representation. You can only use generalizations that are allowed within the H that you chose or within the language that you chose. But there would be times when there could be more than one way of generalizing, and then we will have to include all of them. As long as they're not related to each other. If they're related to each other, if one is a generalization of the other, then you use only the minimal one. But if there are two that generalize in different ways, we will see that example soon, then you have to include them both. Yes?
So can't we include like two examples, like one with the normal and one with the high, instead of making it don't care?
Can you include, instead of don't care here, why don't you make... But let's say here, suppose you're asking if you can have two things. One is sunny, warm, normal, strong, warm, same. And the other is sunny, warm, high, strong, warm, same. Is that kind of what you're asking? Can we do that? Include these two members in S instead of this one member in S. Does anybody have a problem with that? Please?
The second one is two members. It's not general than S1.
The second one is not?
It's not more general than S1, so it can have both.
The second one is not more general than S1. This one is not more general than S1. It's true, but that's not really, you don't really need to be more general than S1. What is the definition of S? The first part of the definition is S consists of members of the version space. Are these members of the version space? How is the version space defined? All functions that are consistent with all the training data. Is this function consistent with all the training data seen so far? No, it's not consistent with the second example. Is this function consistent with the training data seen so far? No, it's not consistent with the first example. Right? Did I get this right? In normal? Yeah, this one is not consistent with the second example. This one is not consistent with the first example. So these two hypotheses are no longer members of the version space. S and G must consist of only members of the version space and only the extreme members. Okay, so it turns out we were lucky again. There's a single way of generalizing minimally from here to here to accommodate the two training examples. So we're good in the second example. Third training example is negative. Now we have to invert what we're doing. Now we'll start with S, that's the easiest part, and G would be the hardest part. With the negative example, you go to S and you just throw out anything that's not consistent with it. Looking at the third training example, and remembering that it's negative, can you tell me which members of S are not consistent with it? To do that, you take one at a time. Well, there's only one. So you take that one member, and you ask yourself, what does it say about example 3? Does it say yes or no? If it doesn't say no, it's inconsistent with it. Does it say yes or no? No. It says no, right? I just boasted that it is able to say yes only for the first two examples and no for everything else. So it is consistent with it. You don't need to do anything. Now we take this negative example to the G front. And we first identify any member that is inconsistent with it. There's only a single member there. Is it consistent with it? I hear some mixed views, mixed opinions here. Could everybody please form their opinion? Yes or no? No, it's not consistent. It's a negative example, and this says yes to everything. So of course it'll be inconsistent with it. Now we need to specialize. The opposite of generalize. It's not generalize in the general sense of machine learning generalization, but making more general or making more specific. We need to find the more specific variance, minimally more specific variance of this hypothesis. How do we make this minimally more specific in a way that makes it consistent with the third example? That's a little tricky. Think what's the minimal change you can make to this to make it agree that the third row should be no. Please. must be sunny. Okay, so you take the first attribute, I assume you meant the sky, right? You take the first attribute and you convert it from a don't care to a sunny. And you leave all the other attributes the same. So you have sunny, don't care, don't care, don't care, don't care, don't care. This is a minimal specialization of this one. It's one step. And what does it say about the third row? It says that it says rainy there. It says out, no, which is good. Any other ways of minimally making the third, minimally making consistent with the third example? That's all the way at the end, please. I can't hear you. Can you speak louder, please? Say it again and louder. Warm, temperature warm. Same idea applied to the second attribute. You keep all of these the same, except you take the second attribute and you make sure it disagrees with the second attribute of the negative example. So this would be warm here. And now you have 4 of these question marks left. So this is also a minimal specialization of this, and it makes it consistent with the third training example. Well, we can do it with all 6 attribute positions, right? So the third one would be don't care, and then under normal, under humidity, because it says hi there, we should say normal. Now we have 3 more question marks. And now we have 1, 2, 3. And the 4th one, wind is strong, so we will make it weak. 1, 2, 3, 4. 1, 2, 3, 4. The next one would be the water is warm, so we will make it cool. And the last one would be 1, 2, 3, 4, 5. And the last value, it's change, so we will make it same. So we now have 6 members, or at least potential members, in G3. These are the 6 minimal specializations that are consistent with the third example. But remember, there were several other conditions that had to be met. One of them was that each such member has to be connected to some member of S. You remember that from the algorithm description? Connected via these arrows means it's more general than some member of S. We're lucky that S has only one member. So all we have to check for each one of these is it more general than this member? If there was more than one member here, it would be enough, it would be more general than one of them, connected to some member of S. But there's only one member. So, is this more general than this? Yes. You can see how we'll go in the other direction. These just get relaxed into question, this one gets relaxed into question mark, and this and this and that. So this is okay on this front. Is this more general than this? Yes. Is this more general than this? No. This has normal here, and this has a don't care here. So this is not more general than this. This is not more specific than this. So this goes out. What about this one? No, this has weak here, and we have strong here. They don't have the substantial relationship. This goes out. What about this one? Cool versus warm here. There's no way to generalize from this to this. So this goes. And this is same, and this is same. That's okay. So the second criterion we had ruled out, 3 of the 6, we're left with 3. There was one other condition, and that is no 2 members of the resulting S can be related to each other with an arrow. neither one should be more specific than the other. No two should be one more specific than the other, right? That condition holds here. There's no relationship between these two. There's no substitutional relationship. So we have our G3. I forgot that we also have our S. I didn't mention S3, right? We looked over S first and we said it was consistent. Is that right? Yeah. Okay, I'm a little over time, but let me just tell you quickly that the fourth training example is positive. If you go over the algorithm, and I encourage you to do that, and you will need to do some of it for your homework, it does make some further modifications to either S or G. I can tell you what it is, and maybe I shouldn't. It's all in the book. What you end up in the end with is exactly the version space example that I showed you before, with 6 members, 1 member in S, 2 members in G, and 3 members that are implicit. They're nowhere in our algorithm. 3 may look like a small number, but when you go out to the real world and you have hundreds of attributes, you will have an exponential number of implicitly described members. Alright, thank you. Homework is out, due a week from now, before beginning of class.